So part 1 says determine if each type of account describes simple interest or compound interest. Simple or compound. And we want to kind of explain our reasoning behind that. So we're going to start off and make a table out of these numbers that we're given. Andrew deposits $300 into his account. So on day 0 in his account, we plug in 0 and we get $300, the amount in the account. After 1 year has gone by, how much is in his account? And it goes down to the 3rd year, I think. $312. And how much does he have in his account on the 3rd year? So this is a really basic account, right? Can you guys tell how much he's earning each year? So all of those are the same. And so we're going to say that this is simple interest. Let's go ahead and create another table. Years on one side and the amounts. Maryland deposits $600. And it does say how much interest each of these people are gaining. We don't really have to look at that on these. We're just concerned with how much money goes in the account. So after 1 year, how much money is in the account?
$600.
And I think it goes all the way to 3. So they're just in order. 618.14. And then the last year, 627.41. If we were to take year 1, subtract year 0 from it, how much interest did he make, or she? And we're going to keep on finding differences. So the single digits, or the whole numbers, is staying the same. It's 9 each time, adding 9. But there's a little bit more each year, right? What's 41 take away 14? I think it does end in a 7. And it's a 20, 27, yeah. Not the same, right? And so if you sign up for a bank account and they give you simple interest, that means you're only earning interest on the initial amount that you put in there. If you take 2%, which is really multiplying by 0.02, so if you take 300 times 0.02, it gives you $6. You're getting $6 additional each month. So you're not gaining money off of the interest from the previous year. I'm thinking that if we were to take this 1.5, change it to a decimal, so it would be 0.015, multiply it times 9, and I'm thinking you're going to get 0.14. So the reason why this person got more interest the next year is because there's $9 more in there. And so 1.5% of 9 is 14 cents. And then the year after that, so it keeps on adding to itself. Compound interest means you're gaining interest not just on the initial amount, but on the last year's ending amount. We're going to go ahead and do part 2 together. Let's see here. For each function, identify the y-intercept, and we got to identify its meaning. Determine if the city's population is increasing or decreasing. So we're given an exponential function, and the meaning right away, you guys don't have to write this each time, is the y-intercept is where we start. It's the starting point, because the x value, what is the x value of the y-intercept? So if you've got the y-axis, which is right down the middle, all the points that are right down the middle, they're not positive, they're not negative. What's the only number that's not positive or negative? 0. So we're going to take our function, population, as a function of time. And when we get to that t at the very end, we're going to plug in 0. That's going to give us our y-intercept. Nice, using 0 to plug things in. What is anything to the 0 power?
1.
So this is going to turn into 1. And then what is anything times 1? Itself, right? So this number is your y-intercept. As you guys are doing these, don't worry about plugging in 0. Interpret the meaning. Well, the meaning is it's our starting point. And sure enough, our town, Millville, is going to start off with 4,000 people. I think about half the size of Bloomfield. So it's the starting population, starting point. The next thing we need to determine is whether our population is increasing or decreasing. When we plug in future years, t equals 5 or 7, we want to know if our population is going to be above or below 4,000. So first, just start by plugging in any number for t. Say 5 or 7, any positive number down the road. What would be 1.3 to the 5th power? I don't even know. It's your calculator would do a better job of telling you what it is. It was 1.03. And we're raising it to the 5th power.
It is 1.157.
So 1.15, that was close. So that number, it grew. We were multiplying by 1.03, but now we're multiplying by a little bit more than that. So if we're multiplying by a little bit bigger number, it should make sense that our 4,000 would get bigger, right? So it turns out if our base, and your base is this number, remember the base is what the exponent gets raised to, or what is getting raised to the exponent. If your base is greater than 1, then that means increasing. Because if we take a number that's greater than 1, the penny was an extreme example. 2 is greater than 1, right? Multiply it by itself repeatedly, it gets bigger. We're not going to be dealing with multiplying things by 2. Populations don't double every year. So it's going to be a number that's greater than 1, and that'll make it increasing. Those are the two things it asks for. So once you've got those two written down, we can move on to the second problem. Which one of these numbers is our y-intercept?
8,000.
So right away, take that number that's by itself, not raised to anything. I'll wait till after we're done working together, okay? It'll be like a minute. That's your y-intercept. We could plug in 0 for t, for year 0, our starting point. starting point. However, it's just going to give us this number. So the next town, Grand City, is starting at 8,000. And now we look at the other number to tell us whether it's increasing or decreasing. If we take 0.98 and we keep multiplying it by itself, 0.98 times 0.98 times 0.98, is that going to get bigger or smaller? It will get smaller as long as it's less than 1. If it's right at 1, what do you get when you multiply 1 times 1 times 1 repeatedly? Nothing ever changes it, right? So no change would be base of 1. So here's the little part that you can refer to. If base is less than 1, then we're going to say it is decreasing. So the first number is your y-intercept. Your second number, you look at it, and it tells you greater than 1 increasing, less than 1 decreasing. These go by really quickly. So you can either continue working on part 2 on your worksheet, or knock out part 1 first. Again, part 1, you're creating tables and seeing if the interest changes. If it changes, we're going to call it compound. If not, it's simple. Go ahead and get going on your worksheet. Let me know if you have any questions. All right, before we go on to the part 3, I want you guys to take a look at, let's do number 6 together on the part 2. So our y-intercept is one of these numbers. Which number is the y-intercept?
109.75.
So picking that number out right away is really straightforward. And then taking a look at the other number, it's going to tell us whether this population is increasing or decreasing. Is that population going up or down?
Down.
So that number is, since 0.9995 is less than 1, then we're going to say it is going down or decreasing. Just comparing it to 1. If it's greater than 1, it increases. If it's less than 1, it decreases. So I want to give everybody a chance to kind of realize how easy those last ones are. We are going to move on to part 3 on our notes. So it's still the front side. And we're given a town with a population, and we're telling how it's changing. And so actually, let's go ahead and take a look on part 3 at number 2 first. And we need to come up with a function. So in your previous problems, our functions are named P for population. So P is a function of T for time. It's years, but we don't like to use Y because Y is generally our output, and it gets confusing if we're saying we're plugging in Y and getting a Y, and Y is actually our X. So that's why we use T for time instead of Y for years. Let's see here. Yeah, let's go ahead and plug in our starting point. What is our starting point? That's the only real number of people that it gives you, right? 20,750 people. And then we are going to multiply it by something. There's going to be 2 numbers that we put in here, because if we were to just take and multiply it times 2.7, well, multiplying it by 2 would double it, right? So our town would go from 20,000 to 40,000 people in 1 year. 2.7 would probably kick it up to like 50,000.
What about 2.75?
That would go even higher, right? Anything above 2 is going to increase the way that our penny that doubled every day increased, right? Towns do not grow like that. 1 year, it's at 20. The next year, it's at 50. The next year, it doubles again. It's at 100,000. Then 200,000, towns don't grow like that, right? And so we need to take and make this number a lot smaller. Since it says percent, per means compared to or divided by. And cent, what number do we mean when we say cent? How many years are in a century? 100. How many cents are in a dollar? 100. So when we say percent, we mean divided by 100. So you're always going to take that number with the percent sign behind it and divide it by 100. It makes it smaller, and it does it by moving the decimal point twice. So we need a placeholder 0, and we need a dot in front of there. So this number, when divided by 100, turns into 0.027. Now, if we were to just take and multiply this by the population, it's going to go way down, right? We want it to increase. And so we're going to take that number and add it to 1. So put 1 plus, and then the percent divided by 100. So 1 plus 0.027. It's a 7 on the very end there. And then there's one last little thing. This is not an exponential equation until we give it an exponent. That exponent is the variable, so it's got a t up there. So this looks a little bit more complicated than it needs to. We can actually add these two numbers together in our final version. So let's go ahead and start writing our final function. Population as a function of time starts with that 20,750. And then we're going to multiply it. When we add these together, we're just going to put that 1 in place of the 0. It turns into 1.027. And what do we raise it to? Kind of hard to see over here, but we had a t above it. Keep that number raised to the t. And so if we multiply this by 1, nothing happens, right? 20,750 times 1 stays itself. We did that. We multiply by 1. So we've got the original population. And then if we multiply it times 0.027, that'll tell you how many people were added to it. So that gives you the amount of people added to it. If we do that once, that's 1 year. If we do that twice, it's after 2 years. And so all we have to do is plug in t for the number of years, and this will tell us how many people are projected to be living in that city. Let's see here. Let's go ahead and take a look at problem number 1. And so the very first thing I'm going to do is take a look at my percent. What am I going to do when I find that number with a percent behind it? Take that and divide it by 100. 1.5 divided by 100. Anytime you're dividing by 100, if you're multiplying by 100, we would change the decimal to make this a bigger number. Since we're dividing by 100, we move the decimal twice. This would be, moving it once would just be a decimal in front of the 1. Moving it twice, we need a placeholder 0. And you might as well throw another 0 in front of there. You don't have to. But it'll keep you from getting it confused with the multiplication dot, which is easy to do. So we have transformed this number. We're going to use this number as we're creating our equation. Again, let's say that this is a function called population, where we're going to plug in t for time. And what's our starting point? $15,000. And you're always going to have 1 plus or minus something. And whether we add or subtract, remember, so if we're multiplying a number less than 1 by itself, it's going to go down, right? So here it says decreasing. So we want our number to be less than 1. It needs to be go down by 1.5%. So we're going to subtract. Whenever you see decreasing, that means you're going to subtract. We saw increasing. You can barely see it over there. When we saw increasing within the problem, then we needed a base that was larger than 1. And so we added right there. So identifying that population is going down means we need to start with 1 and subtract. And then we're just going to plug in the number that we started as a decimal and divided by 100. So if I have room, I'm going to put 0.015. And then what's the very last thing that I need to do? Put a little exponent, a little t up here. I can do what's inside the parentheses, so to simplify this function just a little bit, I'm going to go ahead and rewrite it. And this one, let your calculator do the work. When you're taking 1 and subtracting a very small number from it, it's easy to mess up. It's going to be 0 point something times 0 point, and what is it? Take away 15 thousandths, which is a little bit more than taking away 1/100, or 2/100, yeah, a little bit more than 1/100. So it should start with a 0.98. Yeah, so 1 minus 0.015 gives us 0.985. And the very last part, we've got to put that little t up there so we have somewhere to plug in the number of years that we want to know, after so many years, how big that town is. So I'll let you guys go ahead and work on the 4 problems like this on your worksheet. The key here, 2 keys I'll leave you with, is taking your percent and dividing it by 100. And then the other key is deciding whether it's increasing or decreasing, adding, subtracting accordingly. The rest of it's plugging in what you see from your examples. Let me know if you have any questions.